Hi guys, it's Mrs. Allison. Today we are going to focus on a more general topic of power series. So yesterday we looked at Taylor and Maclaurin series, which are a very specific type of power series. And we today are going to look at the more general form of just a power series. So the definition of a power series is an infinite series that's centered at C and can be written in the form of the sum from n equals 0 to infinity of some function a sub n times x minus c raised to the n. And this center that we talked about yesterday, the centered at c part, is represented by this minus c here. So we can think of a power series as a function of x. So some function f of x equals the sum from n equals 0 to infinity of a sub n x minus c to the n. A sub n is a sequence of constants, really, and are called coefficients of the series. And as I said before, Taylor and Maclaurin series are actually very specific kinds of power series. Now, one of the things we're going to focus on is the domain of the function. And the domain of the function of a power series is the set of x for which the power series converges. So some functions don't generate a Taylor polynomial. Some of them, we can't get a Taylor polynomial at C because the function or one of its derivatives doesn't exist there. So let's look at some problems or some functions that cause problems. And I want you to determine which functions actually give you problems and where the problem is at. So hit pause and see if you can walk through some of these examples and just determine where there might be a problem with the function. All right, let's try the first one. If we look at the function y equals the square root of x minus 1, centered at x equals 2, the first thing that I would do is look at the domain of the original. And if we look at the domain of the original function, this is a square root function, and my domain is where x minus 1 is greater than 0 or equal to 0, which means I want x to be greater than or equal to 1. So my domain goes from 1 to infinity. That includes 2, so I'm okay with it being centered at 2. If I look at a derivative of this, let's say I take a derivative. Y prime would be 1 over 2 square root of x minus 1. And I look at the domain here. The problem is x minus 1 can no longer equal 0. It just needs to be greater than 0 because we can't have a 0 in the denominator. And if I solve this, I get x is greater than 1. But x equals 2 is bigger than both of those. So it is possible. This one doesn't have any problems at x equals 2. So I could keep taking derivatives of this. We're just going to keep getting more and more powers. But I don't have a problem at 2 because my domain is going to be x is greater than 1, and that works. I didn't ever write this domain. This would be 1 to infinity. Lost that parenthesis, but that one works. All right, so if you weren't fully understanding what it meant to look for problems, now you've seen an example, hit pause and try the rest. Let's look at the domain of natural log. We know that the argument of a natural log has to be greater than 0. I can't take the natural log of 0. And so we would get that x needs to be greater than 1. So the domain here would go from 1 to infinity. And if I take my derivative of this, we know the derivative is 1 over x minus 1. And the only issue with domain here is that the denominator can't be 0. So it can be anything else. Actually, it's a better derivative or a better domain here, that x can't be 1. But the problem is it's centered at x equals 1. And while 1 doesn't even work over here, it doesn't work in the derivative, and therefore this function is not possible at x equals 1. Okay, what about the next one? This one, I didn't even need to take the derivative on this one. If I see that it does not work in the original function, it definitely does not work in the derivative. it doesn't matter. We won't even need to go to the derivative, I guess we should say. So if we look at C, C is another example where we don't even need to find the derivative of this, because if I look at my domain of this function, y equals the cotangent of x, I'm just going to rewrite it as the cosine of x over sine of x. Why would I do that? Because if I look at my domain here, I know I have an issue where sine of x equals 0. And to think about where sine of x equals 0, it's at 0, it's at 180 if we're doing degrees. We typically do radians in calculus, so it would be 0, pi, 2 pi. The problem is it's centered at 0, and so therefore this one is not possible. It is not possible at x equals 0 because it's a domain issue. All right, D. If we look at D, my domain here, I'm going to go ahead and take the jump just straight to the domain. I can be from -1 to infinity. So centered at -1 right now is not a problem. If I go and take my derivative of this, y prime equals 1 over 2 square root of x plus 1, here I have a problem. At -1, this makes my denominator 0, so therefore it's undefined. At x equals -1, which means I have a problem, therefore this one is not possible. At x equals -1 rather. So if this happened to be where it said it was centered at +1, we wouldn't have a problem. We could go forward with that. But the problem is I'm not going to be able to write a Taylor polynomial. I'm not going to be able to turn this to a power series if it's centered at a point that causes a problem in the domain. Looking at E, again, my domain here is from +1 to infinity. It's centered at 0. I don't even need to worry about it. Taking the derivative, it's not possible with the original function. And therefore, I don't have to worry about that one. So I could not turn that into a power series. Next one. Here, my domain of my original function is that x cannot be 3. And if I take my derivative, I would get 1 over x minus 3 squared. And that has an issue again at x can't be 3. So my domain is still that x cannot be 3. Well, this is saying it's centered at 4. And therefore, even if I were to keep taking my derivatives, which just means the power of that expression of x minus 3 would keep going up in the denominator, it's still going to be possible everywhere when x equals 4. Possible at x equals 4. Now, why did we go through that? That seems pretty trivial, but being able to determine the domain of a power series is a big concern. Every power series converges at its center. What we know is we can't even write a power series if it's not convergent at its center. So we are going to choose centers that work for the particular function. So if we have a power series that's centered at 0, we can assume that it converges at 0. If we have a power series centered at 1, we can assume that it converges at 1. Those are important ideas of domain and power series. So that leads us to our next topic, the convergence of a power series as a whole. So there are 3 possibilities. The first is that it converges only at the center. So go back to yesterday and we picture that cosine graph and we had that horizontal line. That was the very first thing we looked at with that cosine graph. In that situation with that power series, which was y equals 1, it only converges at 0, where that line is 1. So it is possible that a series only converges at that center. The next possibility is that the series converges absolutely for all x. And the third possibility is that there exists some number, r, we're going to call it, that is greater than 0. And it gives us 2 scenarios. If x minus c, or the absolute value of x minus c, is less than that r, then we say the series converges absolutely. But we say the series diverges if the absolute value of x minus c is greater than r. So what is r? R is what we call the radius of convergence of a power series. So there's the three possibilities. The series converges only at C, the radius of convergence is 0, meaning there is no area outside of the center that converges. But if the series converges for all x, the radius of convergence is infinite. Now, if the set of values of x for which the power series converges is finite, but is bigger than the center, then that's what we call the interval of convergence. So those are the definitions we're going to work on. Now, here's what we're going to do to test for convergence. Okay? Typically, when we test for convergence on a power series, the ratio test is usually the best. Now, sometimes the root test works really well, but basically the ratio test is the one we're going to go to. It's going to be our go-to. And what we're going to do with the ratio test is we're going to use it to find the radius of convergence. Now, what's going to happen is we're going to get an expression, not a numerical value. We're going to get an expression that we can use to determine this radius of convergence. Now, with that expression, we also have to test the endpoints to see if they're included in the interval. And oftentimes when we test the endpoints, we end up using other tests besides the ratio test. Now, the whole point is to look for convergence. So we're going to go back to those same rules that we used before, the same tests that we did in that last unit, to determine our radius and our interval of convergence. So let me walk you through a problem. This problem says find the radius of convergence and the interval of convergence. Be sure to check the endpoints. I wish there was a way I could erase something that was typed, but I cannot. Lots of typos this time. Okay, here's what we're going to do. First thing I want to point out is a couple key features in here. One, this happens to be a power series. Why do I know that? I know this is a power series, and you don't have to write this down necessarily, but I know this is a power series because there's some expression with x in it raised to the n power. Okay, so because I know it's raised to the n power, I know this is a power series. A couple other things I know about this. This particular power series happens to be centered at x equals 2. Why do I know that? Well, I know it's centered at x equals 2 because this in here says x minus 2. This c value is our center. I also know that my a sub n here is 1 over n. Now, those aren't necessary to be able to find the radius and interval of convergence, but just being able to recognize that it is a power series will come in handy. Okay, so the first thing that we're going to do is we're going to do the ratio test. We're going to do the ratio test to find our convergence, our radius of convergence. And remember, the ratio test says this. We're going to take the limit as n approaches infinity of the function at the next term divided by, I'm going to use multiplied, so I'm going to do the reciprocal, divided by the original. And remember, what we would do then is we would simplify this just a little bit. So we have the limit as n approaches infinity of x minus 2 to the n times x minus 2 over n plus 1 times n over x minus 2 to the n. And we would do this because we know these terms cancel. Unfortunately, nothing else cancels, but it leaves me with this expression. I've got the expression, the limit as n approaches infinity of x minus 2 times n over n plus 1. You'll notice that this says the limit as n approaches infinity. You'll notice x is not a part of this. So that expression x minus 2 is actually not going to be part of that limit. So what I'm going to do is I'm going to pull the absolute value of x minus 2 out front, almost as if it's a constant, because it's not part of this limit. And if I take the limit as n approaches infinity of n over n plus 1, what do I get? Well, you'll notice the relative growth rates are the same. And so what I get is this x minus 2 that's in front times 1, because this limit right here is just 1. Okay, so I have this expression then. All of this to say that my result is the absolute value of x minus 2. Okay, let's go back to that ratio test. When does it say the ratio test converges? Remember, it says that the ratio test converges if the ratio is less than 1. Well, that gives us a problem. The problem that I have is that I want x minus 2 to be less than 1. Well, I want the absolute value of x minus 2 to be less than 1. Rewriting this as an algebra problem, that says that we want x minus 2 to be between positive 1 and negative 1. So I'm going to go ahead and solve this. And solving this by adding 2 to all sides, we get this, adding 2. I forgot to add the 2 part. Oops, would be 1. I get this interval. The problem is I'm not quite done with this interval. This interval says that I'm going to be between 1 and 3. What it also says is that my radius, and we found our radius right here. When we set up this problem, we get a radius of 1. Now here is the next part that we talked about. If you look up here, one of the comments I made was that you must check to see if the endpoints are actually included in the interval. Even though when we do the ratio test, we get this interval to be just from 1 to 3, what we need to do is we need to test those endpoints. Okay, well, I wrote kind of big, so I'm going to move over to the side here for just a moment, sorry. And I'm going to test these endpoints. Okay, so in testing these endpoints, here's how I'm going to do that. I'm going to let x equal 1 be one of my endpoints. And when x equals 1 is one of my endpoints, and I substitute in 1 for x, I get this expression 1 minus 2 to the n power over n. Simplifying it, I get the sum from 1 to infinity of negative 1 to the n over n. We've seen that before. What kind of series is that? It's an alternating series. So now I'm going to go through the idea of my checklist of an alternating series. Okay? Is it alternating? That's the first thing I'm going to check. Yes, alternating. Is the limit as n approaches infinity of 1 over n equal to 0? Yes, we check that off. Is it decreasing? Meaning if I take the n plus 1 term and I compare it to the n term, is it getting smaller? Yes. So what we can say is this converges by the alternating series test. And because the endpoint converges, because we can say this endpoint converges here, because we can say this, I am going to include an equal part of that 1. So I need to test the endpoints to see if my interval includes 1. Okay, so now let's test my next endpoint. If I let x equal 3, I would get 3 minus 2 to the n power over n, which is equivalent to 3 minus 2 is 1 to the n power over n. And it looks really close to an alternating series, except it's not alternating. It's just that harmonic series. And I know this diverges by the p series. And therefore, I do not include 3 in this. I don't go and change this to be equal to 3. It's only equal to the 1. So here's what I've got. I have that my radius is 1. We just say r equals 1. And I know that my interval goes from 1 to 3. 1's included, 3 is not. So this is what we call my radius and interval of convergence. All right. Hit pause and try the next example. Okay, again, I'm just going to point out some features of this series. We know this is a power series because there is an exponent that is an n. We know that this power series is centered at x equals 0. We know that because this doesn't have an x minus anything. So we'll assume it's x minus 0 to the n power. And we also know that a sub n would be n factorial. Okay, so this is a power series centered at x equals 0. Again, that doesn't mean anything to be able to find the radius and interval of convergence. It's just good habit to be able to recognize these power series. Okay, so I'm going to test for the radius and interval of convergence. So here we go. I'm going to take the limit as n approaches infinity of. I'm going to go ahead and go to the next term there, and then this would be n factorial times x to the n. And we can simplify this just a little bit. So we've got the limit as n approaches infinity. This would be n plus 1 times n factorial, x to the n, x to the first, over n factorial, x to the n factorial. Okay, and seeing this, I see my n factorial goes away, my x to the n goes away, and so really this problem becomes the limit as n approaches infinity of the absolute value of n plus 1 times x. And what that means to me is I can pull out that absolute value of x. It doesn't have any bearing on that limit. So I will do the limit as n approaches infinity of n plus 1. And what is that limit as n approaches infinity there? Well, it's infinity, right? So here's the problem. I can say that this series converges if the ratio is less than 1. Is there ever a chance infinity is going to be less than 1? No. But going back to that very first thing, we said that the power series has to converge in at least one place. And that one place is at the center. So all we can say is that this converges only at the center. What does that mean for us? It means for us that our radius is 0. Our radius is 0 because it does not go anywhere outside of that center before it converges. The only place it converges is at the center. And then the interval is only the value of the center. So if we get something that diverges or appears to diverge according to the ratio test, then it is still convergent, but only at the center. It has to be convergent at the center. Otherwise, you wouldn't have a Taylor approximation or a power series there. Let's move on to the last two examples. So hit pause and try them and just see what you come up with. All right, looking at this letter C, did anybody recognize this particular power series? I'd like to hope that Somebody recognized this after yesterday when I said you need to have these memorized. This is the Taylor polynomial for the sine of x. So let's look at its convergence and interval of convergence or radius of convergence. So let's use that ratio test. I'm going to hit pause so you don't have to see me write the whole thing. I'll write it down and then we can talk about it. Okay, so if I substitute in n plus 1 for each of my n's, it gets a little bit messy, so be very careful in your details. And I get negative 1 raised to the n plus 1, x raised to the 2 times n plus 1 over 2 n plus 1 factorial. And I went ahead and did the copy dot flop and multiplied by that reciprocal right there, so we get 2n plus 1 factorial. I'm going to go and clean this up. Okay, cleaning this up just a little bit, I get negative 1 to the n, negative 1 to the 1, x to the 2n plus 3 when I combine all the like terms over here. 2n plus 3 factorial times 2n plus 1 factorial over negative 1 to the n. And really cleaning that up that way allows me to get rid of that. And that's it at the moment. So let's clean it up a little bit more. Okay, cleaning this up just a little bit more allows me to get rid of this 2n plus 1 factorial. All I did was start with the 2n plus 3, which I'd go down and keep multiplying. So 2n plus 3, 2n plus 1, so it says 2n plus 2, 2n plus 1 factorial, those go away. All right. Cleaning this up. A few things. One, this negative 1 term is going to go away as well because we're dealing with an absolute value. So that negative 1 is going to become irrelevant. Now, the only other thing that I can do now is use my power rules, or my exponent rules rather. And what that's going to allow me to do is I would have x raised to the 2n plus 3 divided by x raised to the 2n plus 1, which would give me the limit as n approaches infinity of x squared over 2n plus 3 times 2n plus 2. Remember that if you have the same base with exponents, you can subtract the exponents, and 2n plus 3 minus 2n plus 1 leaves me with just x to the 2. Now, if I'm taking the limit as n approaches infinity, what I have then is the absolute value of x squared, which will always be positive, times the limit as n approaches infinity of 1 over 2n plus 3 times 2n plus 2. What is that limit? Well, that limit's 0. So what I really have is x squared times 0, because this limit right here is 0. So I get 0. Okay, well, tell me what that means. We know that the ratio test converges if the ratio is less than 1. So if the ratio is less than 1, it converges. Is 0 less than 1? 0 is less than 1 all the time. It's always less than 1. Therefore, this converges for all real x values, which means my radius is infinity and my interval goes from negative infinity to infinity. So this is one particular polynomial or Taylor polynomial that converges when the center is at 0. All right, try the next one. If we look at this next one, it gets a little bit messy, so I'm going to go ahead and hit pause and write the formula out, and then we'll talk. So first I'm going to substitute in my n plus 1 term, so negative 3 raised to the n plus 1, x raised to the n plus 1 over the square root of n plus 1 times, I'm going to go do my copy dot flop, the square root of n plus 1 over negative 3 to the n, x to the n. So let's clean that up a bit. So we have negative 3 to the n, negative 3 to the first, x to the n, x to the first over the square root of n plus 2 times the square root of n plus 1 over negative 3 to the n, x to the n. So I've got some of these that cancel out, so that's pretty nice. So now I'm going to take the limit as n approaches infinity of, what do I have left? I'm going to go ahead and put that as positive 3x. I'm going to put it as positive 3 because it's the absolute value, so that negative 3 won't matter. Square root of n plus 1 over the square root of n plus 2. And since I'm taking the limit as n approaches infinity, I'm going to pull out the 3x. So I have the absolute value of 3x times the limit as n approaches infinity of the square root of n plus 1 over the square root of n plus 2. And if I look at those happen to be, they have the same relative growth rate. So they're growing at the same rate, which means their limit is the ratio of their coefficients, which is just 1. So this expression, the limit as n approaches infinity, is just 1. And so then I get 3x times 1, which means I just get the absolute value of 3x. Okay, now this is going to be a little bit different when it comes to talk about the interval. We know it converges if the absolute value of 3x is less than 1. Now, because the absolute value of 3x could really be separated to say 3 times the absolute value of x is less than 1, and that's the same thing. When I set up my problem, I'm going to look at it this way. This is going to be important. Here's why. When I get my absolute value by itself is when I can determine my radius. As soon as I get the absolute value isolated, this becomes my radius. So my radius, r, is 1/3. This value right here is my radius. When I get the absolute value as simplified as it can be before I need to write it as an interval to solve it, that becomes my radius. So this is my radius of convergence. And now I'm going to go and solve this. If we say the absolute value of x is less than 1/3, then we can rewrite this as x is less than 1/3 but greater than negative 1/3. When we say this absolute value of x is less than 1/3, what we're saying is that the distance x is from 0 is less than 1/3. So it could be positive 1/3, it could be negative 1/3. Now remember, the next thing that we have to do in this problem is to test our endpoints. We actually have an interval where we need to test our endpoints again. So let's go ahead and test those endpoints. So what I'm going to do is I'm going to plug in each of the x values. X equals negative 1/3 into my original problem for x. So I would get negative 3 to the n power times negative 1/3 to the n power over the square root of n plus 1. Cleaning that up just a little bit, if my exponents are the same, so I have in the numerator here, I have negative 3 to the n power and negative 1/3 to the n power. This is the same as saying negative 3 times negative 1/3 to the n power. Well, if I multiply those, what I get is the sum from n equals 0 to infinity of positive 1 over the square root of n plus 1. If I do a direct comparison to the series 1 over the square root of n, what do we know? Well, we know 1 over the square root of n diverges, and we know that is less than that, greater than that, so that has to diverge as well. So this diverges. So I know it doesn't equal negative 1/3. Let's see if it equals positive 1/3, if positive 1/3 converges. So testing this endpoint, we get negative 3 to the n, positive 1/3 to the n over the square root of n plus 1. I'm going to use the same technique I did before in combining the numerator to give me negative 1 to the n which means it's an alternating series now. So let's go through the idea of the alternating series. It's alternating, check. We've got that much. What is the limit as n approaches infinity of 1 over the square root of n plus 1? Well, it's 0, so I've got that part checked. If I add another number to the denominator, will I keep decreasing in value? The answer is yes. So this actually converges by the AST, alternating series test, and therefore when I go to write my interval would be from negative 1/3 to 1/3, but because this converges, because we know this converges by the alternating series test, I need to put an equal sign at the 1/3. So my interval of convergence here would be from negative 1/3 to positive 1/3, inclusive of the 1/3. And this would be my answer. All right, so this is the idea of a power series and how we determine where it converges. There are 3 places. It converges only at the center, it converges for some small interval around that center, or it converges everywhere. And those are my 3 choices. All right, you guys, you have a worksheet for this. Answers are in Canvas, and have a great day.